All right, everybody. Good morning on this strange Tuesday that is actually a Monday. So glad to be here. We'll have back-to-back classes today and tomorrow. All right, well, we are starting chapter 19 today, which is about a subject that we've been dodging for a long time in this class. Back in chapter, I would say 10 of 351, you learned that alkenes, because of their pi bonds, are nucleophiles. And you did a reaction in which the pi bond of an alkene attacked an acid. The pi electrons are the HOMO of that alkene. It attacks the acid, breaks the HBr bond, and generates an intermediate like this. And you learned that the intermediate has a carbocation on the more substituted carbon where it's more stable. And then you went on to have that Br attack the positive charge to generate an addition product where we've added H and Br. In the place of the old carbon-carbon pi bond and the old HBr bond, we have two new sigma bonds, one between carbon and Br, one between carbon and hydrogen. And that was called electrophilic addition to alkenes. And at that point, some of you maybe saw there may have been some example problems in which benzene was a part of the molecule. Nevertheless, you didn't react HBr with the pi bonds of benzene. And if you asked about it, somebody said, well, benzene's especially stable, just don't worry about it. And today we're going to talk about that, why benzene is especially stable. And the answer is, if you put benzene in HBr by itself, nothing happens. So what you infer from this, the observation is that the pi bonds in benzene are more stable, that is, lower in energy, than the pi bonds in an alkene. And so the first potential explanation for that is pretty simple, and this is something that's been known about benzene from sort of the very beginning of modern organic chemistry. You can draw two resonance structures for benzene in which the pi bonds change their locations. If we number the atoms of the benzene ring, 1, 2, 3, 4, 5, and 6, in the resonance structure to the left, the pi bonds are all between 1 and 2, 3 and 4, 5 and 6. In the resonance structure on the right, that's a 3, they're between 2 and 3, 4 and 5, and 6 and 1. And you have to really appreciate what resonance means, and benzene's a great example to do that. Some of you in the past, and maybe still, are envisioning resonance as electrons switching back and forth. But it's not that way. In fact, let's just zoom in a little bit closer and talk about what we mean by resonance with benzene. One of the things you may not remember from 351 is that double bonds are shorter than single bonds, because you got two pairs of electrons holding the nuclei together. So if we literally meant that there were double bonds between 1 and 2, 3 and 4, 5 and 6 in this structure, and single bonds between 2 and 3, 4 and 5, 1 and 6, what we would be saying is that we expect the bonds between 1 and 2 to be shorter than the bond between 1 and 6. Of course, this other resonance structure tells us that that's not the case. And actually, the true structure of benzene is sort of a hybrid, and you can draw it this way only if you're willing to lose track of the electrons. Some people like to draw it this way with dotted lines, just to indicate that each and every bond in benzene is equivalent and has partial double bond character. And as expected, the geometry of that double bond is the geometry of those bonds in benzene is somewhere between a single bond and a double bond. If you were to do the NMR spectrum of benzene, there is only one kind of carbon and only one kind of hydrogen. Telling you that all of the carbons are identical by symmetry, all of the hydrogens are identical by symmetry. Okay, so there is resonance stabilization associated with benzene, and as you know, resonance is electron delocalization, and that is always stabilizing. That allows electrons to go down in energy. But that's not the whole story, because benzene is even more stable than a corresponding 6-carbon chain that is resonance stabilized but is not cyclic. So this is benzene, and this is called 1,3,5-hexatriene. And benzene is even more stable than 1,3,5-hexatriene, even though you would agree that 1,3,5-hexatriene is conjugated, and there's resonance stabilization there. You can tell because the pi bonds are adjacent to each other. And so it's not just resonance stabilization, and the difference between benzene and 1,3,5-hexatriene is that benzene is cyclic. And we will talk at another time, probably next time, tomorrow, on why being cyclic makes benzene especially stable. But for right now, we want to sort of find a way to recognize molecules like benzene that are resonance stabilized and that are even more stable than their non-cyclic counterparts. So, try to decide whether or not just to tell you the story before we even get to recognizing. What the heck. All right. So where does benzene's special stabilization come from? Going back to a pi bond, if you think about where a pi bond comes from in terms of molecular orbitals, we get a pi bond by adding 2 p orbitals together with the same wave function sign. So we get a pi bond by adding 2 p orbitals together. What we get out of that is an orbital that looks, we can draw it schematically side by side with the 2 p orbitals together. We're not going to worry about the pi star in this particular discussion. And if we were to look at what that looks like in our alkene that we drew over to the left, if we were to look at that from the side, it would look like this, with a lobe of electron density below the plane of the sigma bonds and a lobe above the plane of the sigma bonds. If we looked down on this molecule from above, we would see that continuous lobe hovering over the sigma bonds and then below the sigma bonds. So that's what a pi bonding orbital looks like. And if you do, you can use similar sort of approach to think about the pi orbitals in benzene and in 1,3,5-hexatriene. So just looking at the linear 6-carbon hexatriene, you've got 6 sp2 hybridized atoms, right? And this pi bond comes from overlap of a p orbital on this carbon with a p orbital on that carbon. Maybe we'll number the carbons 1, 2, 3, 4, 5, and 6. Similarly, there's a p orbital on carbon 3 and a p orbital on carbon 4 that make that pi bond, and then a p orbital on 5 and a p orbital on 6 that make that pi bond. When you have more than 2 p orbitals that are on adjacent atoms, you've got something that's called conjugation. You learned about that in 351. Conjugation is a precursor or a prerequisite to resonance. Conjugation equals basically a continuous, and actually the word we want is contiguous. That means adjacent string of p orbitals. So we're going to view 1,3,5-hexatriene from above, And I'm just going to draw the lobe of the p orbital that we can see. And of course, there's another lobe below the plane of the page that for the sake of this discussion, I'm not going to draw. And hopefully that's okay. We're just looking at the top side of those p orbitals, okay? And I'm not drawing in wave function sign yet. We're just thinking the pi bond comes from these two p orbitals. The pi bond here for between 3 and 4 comes from these two p orbitals. The pi bond here between 5 and 6 comes from those two p orbitals. But you can see right away that the p orbital on 2 is also adjacent to the p orbital on 3, right? And the p orbital on 4 is adjacent to the one on 5. So in the same way that the p orbital on carbon 2 can interact with the one on 1, it can also interact with the one on 3. When you have a string of adjacent p orbitals on atoms like this, you create conjugation, and in conjugation we mix those, in this case, 6 p orbitals together, and we do the maths of MO theory, and we get 6 pi molecular orbitals out. And the lowest energy one is the one where we add them all together with the same wave function sign. Does that sort of make sense? So we get one big continuous orbital. If I were to draw that sort of on the structure, show you what, no, that's too many atoms, isn't it? 1, 3, okay. If I were to draw that sort of lined up on the structure, the new pi orbital that we made would look like this, a big cloud of electron density above the plane of the pi bonds with the same wave function sign, 0 nodes. And then the one below the plane of the page, which I am going to draw now, would have opposite wave function signs, so we'll color that pink. So that's the lowest energy orbital that you get from 135 hexatriene. It's got 0 nodes in between the atoms, and it shows you that a pair of electrons in that orbital, which we will call pi 1, would span the whole carbon chain. We're not talking about individual pi bonds anymore. We're talking about a single pair of electrons that's delocalized across the whole chain. All right, that may be new to you. It may look vaguely familiar. We don't need to get too deep into the weeds on this, but it's important to understand what we're doing here is going to help you understand why benzene is a little bit different. Questions so far? Yeah.
So you said 6 pi molecular orbitals, but it seems to me that you can only make 5 different pi bonds in that atom, just looking at it. There's only 5 bonds, so you can put those.
Right. Well, let's see. There's 6 different atoms. We're going to combine 6 p orbitals together in basically all possible phase combinations, or all possible combinations of wave function sign. And you will see that, I mean, if you want to, we can go through it pretty quickly, but you will see there are actually 6 different ways we can do this. This is the lowest energy one. This is the one with 0 nodes. The highest energy one is also easy to see. I'll call this pi 6. You can rank these orbitals in energy in terms of the number of nodes. That is a place where the wave function sign switches. So the highest energy orbital looks like this, and there are switches in wave function sign, or nodes, which I'll sort of highlight in blue here, between each atom. So the highest energy orbital has 5 nodes, whereas the lowest energy orbital has 0 nodes. And we're going to get the remaining combinations. We don't necessarily need to go through that, though I'm happy to show you some of them, but we're going to get the remaining combinations just by figuring out all the possible symmetric ways to put nodes in the molecule. So if you were sort of predicting, okay, what would be the next one, the next higher in energy one would probably be, we would call it pi 2. It's probably got to have just one node, one place where wave function sign switches. And if you were going to pick that spot, and you knew it needed to be somewhat symmetric, you would put it right in between atoms 3 and 4, and you'd have a continuous lobe of electron density here and another here with a node in the middle. of course, this pi 2 that I've just drawn, this is the one we get by adding 3 p orbitals together here side by side, and then 3 here side by side, but with the opposite wave function sign. I'm just completing the drawing, showing a little bit of the lobe below the plane of the page that we can't really see. Okay, others? Yes?
If you have like a node going straight through the bond, like you have in the last two, does that mean that is actually like, I don't know, is that not anti-bonding or something? Like, are they actually connected across those? Can you have the electrons connected?
Yeah, so what does it mean when there is a node? The presence you saw before when we were just thinking about a single bonding interaction, we drew before with the pi bond, the pi and the pi star. And the pi star we got from subtracting one p orbital from the other, so there would be a switch in wave function sign in between the two atoms. And in that case, the node indicated that, whoa, what's blue? I don't know what blue is. In that case, the node indicated that this was an anti-bonding orbital. That's true when you're only talking about 2 orbitals. When you're mixing 6, the first 3 are going to be bonding orbitals, and the last 3 are going to be anti-bonding orbitals. And there's a way to tell whether an orbital is anti-bonding or not. You simply look at the number of times you have atoms together adjacent without a node in between them. Times where atoms are next to each other without a node in between them, we're going to count that as a bonding interaction. I don't think you're going to need to do this, but this will help things make sense, so relax just a little bit. But I'm defining a bonding interaction as a time where 2 orbitals are adjacent to each other with 2 atoms in an orbital, there's no change in wave function sign, there's no node in between them. So in this lowest energy pi 1 orbital, I have 1, 2, 3, 4, and 5 bonding interactions. I'm just going to write that down here. And then I will go ahead and define what I mean by bonding interaction. Times when adjacent atoms have no node in between them. We'll call an anti-bonding interaction. That's going to be the times when there is a node. And as long as an orbital has more bonding interactions than anti-bonding interactions, it's going to be counted as a bonding orbital. So for the simple case of the pi bond, in the pi orbital there's just one bonding interaction, and in the pi star there's one anti-bonding interaction. If we look at the pi 2 orbital that I've just drawn, and I think I'm going to need a little bit more space, so let's drag it down there. I'm going to count 1, 2, 3, 4 times that orbitals are next to each other, that atoms are next to each other with the same wave function sign with no node. And I'm going to count 1 time where, and that's between atoms 3 and 4, where there is a node, where the wave function sign changes. We're going to call that an anti-bonding interaction. Overall, even though we do have a node, pi 2 has 3 net bonding interactions, so we're still going to call it a bonding orbital. Okay, and so we could continue, and we don't necessarily need to draw all of these. That would sort of be beyond the scope of what we want to do. But in the end, for 1,3,5 hexatriene, I'm going to now put them in order of energy. This would be pi 2. We're going to have a pi 3, a pi 4, and a pi 5. You could expect pi 3 to have 2 nodes, pi 4 to have 3 nodes, and pi 5 to have 4 nodes. We don't need to draw them all. You can order them in energy just simply based on the number of nodes. and then you can fill them up with the available electrons that we have that are involved in conjugation. For example, I have in 135 hexatriene 2, 4, 6 electrons in that what we will call conjugated pi system. So now I'll simply fill up the orbitals from bottom to top with the available electrons, and I would see that pi 3 is going to be my highest occupied molecular orbital. Pi 4 would be the LUMO. And periodically, I will write questions on exams where I actually draw these pi orbitals for you, and I say which is the HOMO and which is the LUMO. And all you have to do is count the number of nodes to rank them in energy, then count the number of pi electrons to figure out how many you have, then fill the orbitals up from lowest until you run out of electrons, and that will tell you what the HOMO and the LUMO is. For example, even if I didn't know that this pi 2 orbital was pi 2, I would know that it's higher in energy than this one, which has no nodes. Similarly, maybe I'll draw the pi 3 orbital for you. The pi 3 orbital is going to have 2 nodes. One, let's see, between atoms 2 and 3 and between atoms 4 and 5. And if you drew this orbital, it would sort of look like this with changes of wave function sign every time you go through a node. And remember, what we're saying about these orbitals is this is the wave form adopted by the pair of electrons that is in that orbital. That pair of electrons is delocalized across the whole molecule. What we lose in the MO theory picture is we lose the idea of 2 electrons being in a specific bond, right? These 2 electrons are shared across atoms 1, 2, 3, 4, 5, and 6. These 2 electrons are likewise shared between atoms 1, 2, 3, 4, 5, and 6. They just happen to go through a node in between. These 2 are also shared between 1, 2, 3, 4, 5, and 6. They just happen to go through 2 nodes. Yeah?
What is the fact, like why, for example, in the pi 2, do you draw it in the middle so it's symmetrical? Why does it matter that it's symmetrical?
Why does it matter that it's symmetrical? That's a good question, and some of it comes from the math, which I don't totally understand, so I have a hard time explaining it to you. Other than the orbitals have to follow the symmetry of the molecule. If you look at 135 hexatriene, you would conclude that 1 and 6 are equal, that 2 and 5 are equal, and that 3 and 4 are equal. So that has to be true in every single orbital that you make. Yeah. All right. So notice what conjugation and resonance does for this pair of electrons in the pi 1 orbital. Let's just focus in on the pi 1 orbital. That has 5 bonding interactions, right? Compare that with the simple pi orbital for an isolated double bond. How many bonding interactions are in that isolated pi bond? How many times do we have atoms with the same wave function sign in that pi orbital? Just once, right? So pi electrons in this pi orbital get 1 and only 1 bonding interaction. In contrast, electrons in the pi 1 orbital get 5 times as many bonding interactions. So that gives you a sense for why resonance is stabilizing. Electrons get to delocalize over more space, and they get to experience more nuclei. And that's sort of what we're counting when we count a bonding interaction. So that shows you why this pair of electrons in 135 hexatriene is lower in energy, that is less reactive than electrons in an isolated pi bond. And you can do the math and show that this is the case. All right, so that's all setup. This is a really, when I tell jokes where this is the length of the setup, it never lands. So you got to stick with me. The payoff is coming. It may not be worth it. All right, questions? More questions about this? Yeah.
What
Okay, what do the 4 and 5 look like? You simply got to decide where are the symmetrical places to put the nodes. So I need 3. So I got to put 1 in the middle, right here. And then I got to put the other 2 here. So this orbital is going to look like this. And you can see that it keeps our symmetry rules in the sense that the nodes are in the same places on either side. So that's 3. And then if you want 4, that's kind of tricky. Again, I would never, ever have you try to draw these on your own without any help. And off the top of my head, let's see, 1, 2, 3, 4. I would never have you draw these without help. Instead, I would draw them for you, and you would just pick. You would have to rank them in energy based on the number of nodes. So as long as you can count the number of times wave function sign switches, that would get you where you needed to be. Okay. Right. So now we're going to think about how things change for benzene when we make it a ring. All right? Remember that in benzene, we've still got a bunch of sp2 hybridized carbons. Each of these carbons has a p orbital on it. We could draw those p orbitals looking down from above, just like this. And we could imagine, again in benzene, that we're going to take 6 p orbitals and we're going to get 6 pi molecular orbitals out. And the lowest energy one is going to be the one where we add them all together with the same wave function sign. Okay? That literally looks like what we would get if we took 1,3,5 hexatriene and we folded it back around to make a ring. Okay? But look at what that's done. In this lowest energy orbital for benzene, how many bonding interactions are there? 6. By cyclizing, we pick up an extra bonding interaction. That's why benzene is more stable than 1,3,5 hexatriene. So let me just slide this over a bit because I want to make that point. With benzene, we won't draw all the pi orbitals of benzene, but we'll draw the lowest energy one. This is the one that we drew above, and I'll show you what that looks like. Sort of, it's like a cloud of electron density above the benzene ring and below the benzene ring that sort of takes up all the space inside the ring, above and below. And I suppose if I wanted to be completely accurate, it's a little bit more like a donut. So shoot, I don't like my drawing. Let me try again. We could draw it kind of like this and maybe like this. That may be an exaggeration. If you want to think of it as like a hamburger with the bun on top and the bun on the bottom, and the benzene is the meat inside, that's sort of what this pi orbital looks like. And again, key is that there are, as we've said, 0 nodes that come in between the atoms, and that because of that, there are 6 bonding interactions. And that is more stable than the 5 bonding interactions that we get from the pi 1 orbital. Okay? There's a couple other differences of benzene. Having the molecule be cyclic introduces some elements of symmetry that cause changes in the way the orbitals look for benzene. I will try to illustrate this briefly with the next 2 orbitals. So you would expect that because the pi 1 orbital has 0 nodes, you would expect the next orbital to have 1 node, right? And I told you that symmetry is important here. If you draw a benzene ring, there are actually 2 independent ways you can draw one node, right? You can draw a node that comes and coincides with what we'll call atoms 1 and 4, such that this orbital would look like this. On the right, you'd have a lobe. On the left, you'd have a lobe. And then below the plane of the page, there'd be corresponding lobes with opposite wave function sign. This oops, that's not the right way. There we go. This orbital has 1 node. But there is an independent way that you can draw an orbital that has 1 node, and that would look like this. And the fact that we can draw 2 orbitals with 1 node in 2 different ways is a consequence of the fact that we made this molecule cyclic. One of these is called pi 2, the other is called pi 3. Because they each have 1 node, they are actually equal in energy. If you don't believe that, you can actually count bonding interactions versus anti-bonding interactions. The pi 2 orbital has 2 bonding interactions, which I'm going to abbreviate like that, and it actually has 0 anti-bonding interactions. If a node coincides with an atom, there's no switch in wave function sign in between atoms 6 and 1. So this doesn't count as an anti-bonding interaction. That's probably beyond the scope of what I expect you to do, so you can accept that on faith if you want. Orbital 3 has 4 bonding interactions and 2 anti-bonding interactions, which leads to net 2 bonding interactions, and that's how you know 2 and 3 are equal in energy. So look at what this does for the benzene ring. You have 1 lower energy orbital that has, and we count the number of pi electrons in benzene, there's 2, 4, 6. Then you have 2 higher energy orbitals that are equal in energy to each other, pi 2 and pi 3. So the effect of benzene is to make the effect of cyclization brings the lowest energy pi 1 lower because it's got more bonding interactions. And then it brings these next two orbitals equal to each other. And overall, that means that the electrons overall in benzene are more stable than they are in 1,3,5 hexatriene. And it's because the cyclization allows you to pick up another bonding interaction, and it changes the symmetry of the system, making these the pi 2 and the pi 3 orbitals equal to each other in energy. Now, your text will draw these orbitals for you. The anti-bonding orbitals, there's also 3 of them, and they show up in roughly this orientation, pi 4, pi 5, and pi 6. These will draw sort of a dividing line here between the between the bonding orbitals and the anti-bonding orbitals. And I think that drawing is kind of messy, so I'm sorry about that. Okay, questions about the pi orbitals in benzene? I would not ask you to draw those benzene pi orbitals from scratch at all, but I would ask you to recognize whether 2 orbitals in benzene are equal in energy to each other. That's not that hard, you just have to be good at counting nodes. So look where the wave function sign changes. The reason that you know pi 2 and pi 3 are equal in energy is because they both have 1 node. Another word for being equal in energy, It's a mathematical word. It's called degenerate. And so you'll sometimes hear that doesn't mean they're of dubious moral quality. That just means that they're equal in energy. All right. With that background in place, you'll be able to see some of the reasons why the rules for recognizing molecules like benzene are the way they are. Okay? A precursor, and we're going to talk criteria now, but before we do that, anything else you want to know or any concerns you have about the orbitals? Yeah.
Sorry, just looking at the net bonding interactions, what does that mean?
We're using that to confirm that these two are equal in energy. Really what we're doing is summarizing. I'm giving you sort of a mnemonic device or a tool for determining whether an orbital is a bonding orbital or not. We simply look at the number of times adjacent atoms have the same wave function sign versus opposite wave function sign. Here, these two, oops, that's an eraser. Here, these two have the same wave function sign. That's one bonding interaction. These two do too. That's two bonding interactions. This one is neither bonding nor anti-bonding because wave function is 0 on this atom. So we don't count that. We just leave that off. That's 0.
But like, would that be important to know, like where the bonding interactions are, like during a reaction?
No, would that be important to know where the bonding interactions are during a reaction? No, it's more of a way to just understand. It's more of a way to recognize which orbital is a bonding orbital versus an anti-bonding orbital and which orbitals are equal in energy. In a way, it's exactly the same as counting nodes. Yeah. But what you said about in a reaction, if you were to look at benzene, which pair of electrons, the ones in pi 1 or the ones in pi 2 or pi 3, are going to be the highest energy ones in a reaction? Pi 2 or pi 3. You can't tell which. They're equal in energy, so it's going to be one of them. Yeah. Okay, good. Yeah.
For the anti-bonding orbitals, do they become anti-bonding orbitals once the anti-bonding interactions exceed the bonding interaction?
Yes, do they become anti-bonding once the anti-bonding interactions exceed bonding? Exactly. So I won't draw those, but if you go look in your text and go through that analysis, you'll see that that's exactly what happens. Yeah?
So pi 2 and pi 3 are equal in energy. Are pi 4 and pi 5 equal in energy?
Yes, these two, pi 4 and pi 5, are also equal in energy. You'll see that they also have the same number of nodes. So there's 2 nodes in pi 3. 2 nodes in pi 4 and pi 5, sorry. All right. Okay, so to be like benzene, we've decided you got to be cyclic. You have to be fully conjugated. That is, each atom on the ring has to have a p orbital. And that p orbital has to be able to line up with all the other p orbitals in the molecule. So let's just sort of start keeping track of this. The special stability of benzene, we're going to call aromaticity. And this term has the word aroma in it. And it used to be that benzene has a characteristic smell. And a lot of molecules like it do, and so similar to benzene have a characteristic smell, and so that's where the term originally started. Not every molecule you can smell is aromatic. For example, I think there's a tree by the Marb, a ginkgo tree, that occasionally when it flowers it starts to smell like vomit. What you're smelling there is a small carboxylic acid called butyric acid. That's smelly, it has an aroma, but it is not aromatic. So the term aromatic no longer refers to smells, it refers to being like benzene. At least as chemists use it, okay? So to have benzene's special stability, you gotta be cyclic. We verified that because being cyclic introduces a new bonding interaction. You've got to be fully conjugated. And what do we mean by fully conjugated? That is, you need this, what I've called a contiguous string of p orbitals that can line up with each other, parallel to each other. Orbitals that are perpendicular to each other do not interact very well. We've learned that before with the pi bond. That's why pi bonds don't allow rotation around the carbon-carbon bond, because as you rotate around the carbon-carbon bond, you have to break the pi bond as you bring the p orbitals perpendicular to each other. So to be aromatic, you've got to be cyclic, fully conjugated, meaning you've got to have a contiguous string of p orbitals that can line up parallel with each other. A consequence of this, or a prerequisite to it, is that the molecule is going to be, or at least in the area that's aromatic, it's going to be planar. Okay? Finally, and this is something that you sort of have to accept on faith until you see what the orbitals are doing in benzene, you have to have the right number of pi electrons. What is the right number of pi electrons? Well, notice that benzene has 6. And notice that the MOs of benzene, the MO picture of benzene that we've developed has one lowest energy orbital that can have 2 electrons. And then next, you've got a pair of degenerate orbitals, each of which can accept 2, but you've got a place for 4 electrons at basically the same energy level. What would happen if I only had 4 electrons in benzene? What would that look like? Well, we can sort of imagine that. Let's draw sort of those first 3 orbitals for benzene. Let's figure out how to put 4 electrons in. 1, 2. Now, what do you do when you have 2 orbitals that are equal in energy with electrons? This is something from Gen Chem. Hund's rule, 1 at a time, parallel spins. If you got the wrong number of electrons, you now have a diradical. 2 unpaired electrons, and unpaired electrons are reactive. So, in order to take advantage of benzene's special stability, you have to have enough electrons to fill the lowest energy orbital and to completely fill subsequent degenerate pairs of orbitals, which can each take 2, so 4 total, right? So the rule for benzene, and this is called the Huckel rule, the rule for aromaticity, that's an umlaut there, Huckel, is the right number of electrons follows a pattern 2, 4, nope, not 4, sorry, 2, 6, 10, 14, 18, etc. If you're into series, this would be 4n plus 2, where n equals 0 or positive integers. People get confused about what n means. Does n mean the number of atoms in the ring? No, it's just an integer. So these are the number, and if you think about it, these are the number of electrons that would completely fill either the lowest energy orbital and leave everything empty, or completely fill the remaining pairs of degenerate bonding orbitals. And we'll show you some examples of that in a little bit. In contrast, if you have the wrong number of electrons, so there's an especially wrong number, that would be 4, 8, 12, 16, etc. That follows the 4n rule, where again n is an integer, 1, 2, 3, and 0, and all of that. You have especially unstable character, and that's called anti-aromaticity. And that's where you are reactive almost as though you were a diradical. Classic example of that I've already drawn for you here is the picture for cyclobutadiene. So this is a 4-membered ring. It's cyclic it's fully conjugated, but it has 4 pi electrons. These are the MOs for cyclobutadiene. Your text will teach you a mnemonic device for drawing these MOs. We'll talk about that briefly next time. It's not worth saying a lot right now. This is what the MO picture looks like for cyclobutadiene. This is energy. You have 2 electrons in the lowest energy pi1 orbital, but the remaining 2 electrons go 1 in each of pi2 and pi3. So cyclobutadiene reacts like a diradical. And in fact, even though you've drawn 2 bonds there, the energy for these 2 electrons is right at the level you would expect for atomic orbitals. In other words, cyclobutadiene has 1 pi bond and 2 unpaired electrons in it. It is especially reactive, and we would say it is anti-aromatic. In contrast, as you've seen for benzene, benzene has 6 pi electrons. It's able to fill this one, and then these 2 degenerate pi2 and pi3 orbitals. And so you fill all the bonding orbitals. There's no unpaired electrons. That's aromatic. All right, so a big thing to do is to get used to recognizing and categorizing molecules as aromatic versus not aromatic. And you can do this in all sorts of different combinations. Your text is going to push you on this. There are going to be nuances, which we will talk about in greater detail. Let me give you some examples, and it's always challenging when you start including atoms that are not carbon. So let's just do a couple. The stop sign molecule. Aromatic or anti-aromatic? Anti-aromatic, right. I want you to put an asterisk in your head on all anti-aromatic compounds, because that's not the end of the story, but there's more to tell you, and we'll tell you that next time. How about this? You don't know what to do with that lone pair, do you? Is that part of the pi system or not? And how can you tell? All right, let's look at that nitrogen. What's its hybridization? You would say roughly sp2 because it's surrounded by 3 things, 2 carbons and a lone pair. Okay, where does a sigma bond come from? sp2 on the nitrogen. So we have 3 sp2 orbitals. We've accounted for 1. How about that sigma bond? Also an sp2 orbital. What about the pi bond? Where does that come from? The p orbital on nitrogen. Therefore, the lone pair can only be where? That lone pair is in an sp2 orbital. What is the geometry of sp2 orbitals relative to p orbitals? Perpendicular, right? So that lone pair is actually in the plane of the page, and it is perpendicular. That's a long word that I don't like to write. Perpendicular to the pi bonds. So it cannot be involved in resonance or aromaticity, so that you don't count those. This is tricky. There's no, and I'll take you through a lot of examples, but nitrogens and oxygens are tricky, and you have to work through the analysis bit by bit to tell, are those lone pairs in a p orbital, or are they in an sp2 orbital? If they're in an sp2 orbital, they can't be involved in resonance. So if we don't count those, then we have 6 pi electrons, and the molecule is aromatic. Okay? One for you to wrestle with between now and tomorrow Let me give you a hint. One of those lone pairs counts, the other doesn't. But which one? Feel like Yzma in the Emperor's New Groove. Which one? Which one? Good luck. I will see you tomorrow.